Can you hear me? All right. Well, thank you. Let's see, I just want to turn off some lights here. So, okay, that's good. All right, so let me just organize myself here. So this is a am I going to fight this the whole? Okay. So this is kind of a triply intimidating speaking engagement, being introduced by Bob. You know, first of all, it'll come back. Okay. And then second of all, I think this day, almost exactly 37 years ago, I was sitting about there as a freshman in what was then called H5A, waiting for Mark Strovink to teach me physics. So I was an undergraduate here, actually majoring in, I wasn't a physics major, I was an engineering physics major. I hear the program's still going. It's a wonderful option. You know, so I had a great time here, and it's just fabulous to be back, but it's really strange to be in the front of this room rather than in the back of this room. And I went to, of course, many colloquia, and this room looks unchanged. We have a room like that at MIT called 26100, something having to do with the permitting process in the city of Cambridge, so I'm sure it's the same sort of thing here.
No.
And then, oh, okay, I'll retract that. And then the third thing is I'm coming to talk about dark matter, but I'm coming to really the center of the dark matter world here at Berkeley. You know, Berkeley, University of UC Berkeley has really, you know, led the way in the hunt for dark matter, both in astronomy and in particle physics. So it's really a privilege to come here, but it's also kind of daunting to come to, you know, the place that's really leading. However, you know, MIT rewards boldness, so I will sally forth, and I will give several opinions in this talk, which some may find provocative, possibly even offensive. But I think it's important when talking about science to talk about the whole story of science, which is that not everything you do works out, that there is frustration and sometimes disappointment, but it's really the journey rather than the destination. And I hope to communicate to you how, for me, interesting the journey has been. And I'll tell you up front, I'm not here to announce that I've discovered dark matter, but I've had a really great time not discovering dark matter. So I'm going to start by a little introduction. There are two views of dark matter. Actually, there's a continuum of views, but the two ends of the spectrum I'll indicate using people. So there's on one side the particle physics view, and on the other side the astronomer view. So I'll take the particle physics side. The astronomer I'll identify as Paul Schechter. Some astronomers here probably know Paul. He is probably the most hard-ass astronomer I've ever run into. We talk about dark matter a lot because we both work on it, but from very different points of view. So the Paul Schechter point of view is we know a lot about dark matter. We know how much there is. We know how much makes the universe look the way it is. We understand how the fluctuations of the early universe make large-scale structure. We use lensing as a tool to measure galactic masses. We measure rotation curves. We know how matter and energy are apportioned in the universe to better than 1%. We know how much dark matter is here on Earth. And so astronomers are quite happy with the dark matter situation in a certain way. And they can really use it for their own devices to learn more about what happens in the universe. Just a few things I want to mention. This apportionment, baryonic matter, which I'll sometimes refer to as normal matter, is the stuff that's in this room: protons, neutrons, electrons, neutrinos, photons, all the standard model stuff. Dark matter is other stuff, which will really be the subject of the talk. Dark energy where again, Berkeley astronomers played and particle physicists played a pioneering role. I'm not going to say anything more about, as I'm sure you've certainly had ample opportunities to hear about it here. Secondly, the dark matter density here on Earth, this comes from the particle data book, so it's got to be true. It's about 40% of a proton mass per cubic centimeter. And this is actually frustrating because we know about dark matter because of its gravitational interactions. So we know what the dark matter mass density is, but we do not know what the particle number density is. For that, you need to know the mass of the dark matter particle, and a large part of this talk will be devoted to the fact that we don't know the mass of the dark matter particle. Anyway, you can see this is a pretty precisely known number, so astronomers really kind of feel like, you know, they know what's going on. Now, the particle physics view is we have a much better idea of what dark matter is not than what it is. So dark matter is not any of the 6 quarks, 6 leptons, 4 force carriers, or 1 scalar in the standard model, nor is dark matter a bound state of any of these. It's not charged because it wouldn't be dark if it were charged. Photons would scatter off of it and we'd be able to see it. And it does not carry color charge, or at least not much. And it's cold, meaning that it moves non-relativistically in the current epoch of the universe. So we really do not know what dark matter is in terms of its particle properties. So Paul and I talk about this, and you know, there are places where we agree. And one of the places we agree is that a fence between astrophysics and particle physics is a good thing, and good fences make good neighbors. So we each have our point of view, and we quite happily have breakfast on Thursdays and talk about what we're doing. So the talk is going to be kind of structured around these 2 points of view. And the first part of the talk I want to go through very quickly, because the first part of the talk is largely stuff not done by me and done by people here. So I'm not going to be so audacious to come and explain what your colleagues are doing, because I'm sure they've explained it to you. But what I want to tell you about in the first part of the talk, and this is mostly for students, but also for older people, is the idea that dark matter really shapes what the universe looks like to us. When we look in the sky and look at large-scale structure, what that looks like visually is because of dark matter. And I'll say more about this. The second part of the talk will be the particle physics part, which I've been involved in. I'm going to talk about a series of experiments, not all experiments, in fact, quite a small subset of experiments. But I want to end with a clear statement of where I think the field is in terms of particle dark matter and where we need to be going next. I'll end with kind of that summary and some inspirational remarks for students, because I think this is a wonderful topic. And I met with your great SPS students today just before this talk, and there's a lot of enthusiasm for this topic. And I just want to say it's a great thing to study, and I want to encourage people to do it because it's really unique in the field. Okay, so I'm going to show some pictures and talk about how dark matter shapes what the universe looks like, from the largest scales down to the scale of galaxies. And I'm going to go through the first few examples quite quickly, and then kind of dwell on a fourth example. Okay, so I'm certain you've all seen this. This is a map of the microwave sky taken by the COBE instrument that George Smoot played a huge role in. This is a temperature map, and what it is if you stood here and looked straight up, that would be this point here. If you look out and circle the horizon, that's here, and then straight down is here in some coordinates. And so it's the sphere that's surrounding us kind of rolled out. And this is a temperature map. The average temperature is 2.7 something degrees Kelvin, and what's shown in color is deviations from that average temperature. And the maximum deviation is something like 300 millikelvin. So the fluctuations from normal temperature is very, very high. I mean, I'm sorry, very small numbers. So that doing this experiment was a tremendous feat, measuring these very small temperature deviations on a spacecraft. And the key to this experiment was it really showed that it was possible to do this. Now, the angular resolution of the experiment was about 7 degrees, which is about the size of a patch there. And this was one of a number of experiments starting in the early 1990s. This result comes from 1992, as I recall, at successively higher and higher resolutions, better and better resolutions. So in 2000, another spacecraft imaged the sky called WMAP. And if you remember, the little patch that I pointed to here is right there. And you can see that that is a little blue, still a little blue patch, but it's got some structure in it. And the key to this experiment was the angular resolution was well under a degree, about 1/5 of a degree. And the importance of that is that this light was emitted when electrons combined with protons to make neutral hydrogen for the first time, emitting photons in the process and rendering the universe electrically neutral, so those photons would propagate ballistically through the universe through 13.7 or 13.8 billion years and be detected by us as microwaves because they stretched out as the universe expanded. So this is really an image of what the sky looked like about 400,000 years after the Big Bang. And these patches, which you can see that are about a degree in size, are places where there were overdensities and underdensities of dark matter due to quantum mechanical fluctuations in the very, very early universe. Those quantum mechanical fluctuations, as time passed, grew into the large structures of the galaxy. And those quantum mechanical fluctuations were fluctuations in the dark matter density. So that's a first example on the cosmological scale of how dark matter makes the universe look the way it does. And I tried to show this in a little cartoon. So here we are here. This is 3 billion years after the Big Bang. And this is the shell at the 400,000 years after the Big Bang of the microwave photons. So the photons have propagated in, and these are these little patches of overdensities and underdensities. If you came back in 3 billion years, you would see that this little patch has resulted in an overdensity of dark matter and normal matter, and the normal matter is collapsing in and beginning to form galaxies and clusters of galaxies. And then there are new patches as you probe further and further out, and here's this one just emerging. And as time goes on, these things turn into clusters of galaxies and beginning life as kind of blobs. So you're really looking at a picture of what the universe is going to look like. And then the most recent has angular resolution much smaller than 1/10 of a degree. And that's enough to see overdense regions that have expanded and collapsed several times. And there's a very long story behind this that I wish I had time to tell you, but it's encoded in this 2-point correlation function of this data. And you can see that there is structure at a degree, and then this is an expanding collapsing region, this is a collapsing region, that's an expanding region, and so on. The main reason I'm showing you this is to show you how precise the data is. These points have error bars, and the theory is a parameter fit, but you can see the agreement is very, very high. So I don't have time to tell you the details, but what I want you to understand is that there's a pretty deep mathematical understanding of how dark matter transitioned from quantum mechanical fluctuations to structures that we see in the universe. You can do the same thing by actually looking at galaxies that exist, and those are called that measurement is called the measurement of baryon acoustic oscillations, and you can also see the same phenomenon there. And there's several experiments where Berkeley's playing an enormous leadership role measuring the baryon acoustic oscillations. So that's a first example. The second example is, this is the bullet cluster. Many of you have seen this before. This is actually not such a good picture because it shows 3 different data sets. The sky doesn't actually look like this. This pink region is a data set of temperature map of in X-rays of 2 galaxies that are colliding with each other or have collided with each other. One's going this way and one's going that way, and they just pass through each other. These X-rays are from normal matter gas in the 2 galaxies that collided, heated up, emit X-ray photons. These purple regions are the region where the dark matter is, and the way you discern that is through a phenomenon called gravitational lensing. And this is making use of the way that mass can bend light from objects behind as they propagate to the telescope on Earth. I'm going to skip over this because I want to dwell on the example after this one. I'm just showing this because you have to show the coma cluster in any talk about dark matter, because that's the place where Fritz Zwicky made the first measurements that resulted in the idea that there was missing mass in the universe in the mid-1930s. But what I want to dwell on a little bit is looking at galaxies. So we started by looking at the universe as a whole. So that's the whole universe, dark matter making structure in the whole universe, dark matter running ahead of normal matter in the collision between 2 galactic clusters. So this is dark matter's impact on the galactic cluster scale. Here in the coma cluster, dark matter allows these galaxies that are elements of the cluster to have higher velocities than you would expect, given the amount of mass as discerned from the light. And now I want to talk about galaxies, because galaxies are the smallest scale where dark matter plays an enormous role. And this is Andromeda, which is the nearest galaxy to Earth. It's about a megaparsec away, or 3 million light years if you don't like astronomer units. And Andromeda very literally looks this way because all of this sits inside a halo of dark matter about this big. And in the beginning, the baryonic matter or normal matter was pretty much mixed with the dark matter. As time went on, the normal matter could interact with the other normal matter, emit photons, kick out some normal matter, and lose energy and fall from a halo this size into a structure this size, because normal matter can dissipate energy relatively efficiently through collisions. What normal matter can't dissipate very well is angular momentum. So it collapsed into an energetic state of the angular momentum it had to begin with and minimum energy. So that results in this beautiful swirling disk. There's higher density in here, so there's a lot of stars being formed and bright light, and then here are the spiral arms. But the other place where dark matter makes this look the way it is you can see there's really an edge to this galaxy. It doesn't just get smaller and smaller and smaller as you go out. And this edge is because of the Schmidt-Kennicutt relation, which is an empirical relation between the density in a unit in a large volume of space and the star formation rate. So it's a power law relation between density and star formation rate. But one of the things that I think was Kennicutt discovered is that there's actually a threshold below which stars don't form at all. And that's right where the edge is here. And again, dark matter regulates the gravitational potential that all of this stuff is falling in. And so it regulates the density distribution and makes this very sharp edge. So this is all swirling around. If this were the Milky Way, the Earth would be about here. It takes about 200 million years to go around once. And you can actually measure the rotation velocity by measuring the redshift of light emitted by objects, dust and stars, mainly dust and gas, in the galaxy. And this was actually first done in 1939 by Horace Babcock, and his measurements are shown here. He measured 3 points, one here, one here, and one there. Sorry, 4 points. There's another one there. About 10 years later, Bade and Mayall measured the points indicated with stars. So you can see there. And then Rubin and Ford in 1970 made the measurements that are shown here. Now, what am I showing you? This is distance in minutes of arc. So there's 80. And I've indicated 80 minutes of arc from the center of the galaxy. That's right at the edge, this Kennicott edge that I told you about. And on the y-axis is the velocity measured in kilometers per second. And so what you can see, so this is how fast stuff is going around. What you can see is once you get away, about halfway out from the center, this comes down and is relatively constant way past the visible edge of the galaxy. Now, what you would expect if all the matter in this galaxy were due to the stars and dust and gas that you could see by looking at photons, that once you got outside this edge, the velocity would begin to go down. It's a simple calculation for a massive disk of gas. What's observed instead is that the velocity is constant at about 200 kilometers per second, and that's because there is more mass outside in the form of dark matter, which you really can't see. So it's literally making the galaxy rotate in the way that we see it. And these rotation velocities were made using the redshift, which is the change in the frequency of light due to the motion along the line of sight to the observer. So this thing comes from the way dark matter looks, the way dark matter works. And the way I think about it is, it's like if you were living in your house and suddenly you became aware that there were like, for every person living in your house, there were like 10 invisible people living there. And you couldn't see them, you couldn't hear them, you couldn't smell them, you couldn't feel them. And you only knew they were there because they kind of kept rearranging the furniture. And you take something and you put it over here, and then suddenly it would just be back there because they're doing their thing and you're doing your thing. And the only way you know about each other is through the gravitational interaction of moving things around. So and if you think about it for a minute, if this were really true, if you suddenly thought there were invisible people living in your house, it would be pretty upsetting. And this is pretty upsetting. Now, the reason I added these points here from Babcock was I was giving this talk, or not this talk, a different version of this talk to a group of MIT alumni, and one of them popped up, and I just showed the Rubin and Ford points because that was the best measurement, and we'll come back to that in a minute. It turned out Horace Babcock's son was in the audience, and he got quite upset because he felt that his father, who had made these measurements, had been cheated out of the discovery of dark matter. And so I made it my business to look into this. And what I quickly realized is that when these measurements were made, nobody was using the term dark matter. What astronomers were talking about were missing mass in the galaxy. And the reason the Rubin and Ford measurement was so important was that was the best measurement at the time this phenomenon, which was called missing mass, transitioned from a problem that astronomers had in accounting for the mass and the motions in the galaxy to a particle physics problem. And that's when the name changed from dark matter, from missing mass to dark matter. And actually through the magic of Google Ngrams, I was able to go back and find the first time the words dark matter appeared in print. So this is year along here, and this is percentage of books with either dark matter or missing mass. And and this is not terribly precise because both terms are used also for other things. DNA is apparently filled with dark matter. The dark matter used to be the word for black dust, and Neil Armstrong apparently talks about seeing dark matter on the moon. He's talking about something that's black in the dirt on the moon. He did not discover dark matter either. But what you can see is the term dark matter skyrockets in about 1983, and that's the first time the word dark matter appears in a paper by Joel Primack. I found the term used earlier in 1972 by an astronomer named Paul in the wonderfully titled conference, Confrontation of Cosmological Theories with Observational Data. We do a lot of that. So this is kind of a segue to the particle physics talk, part of the talk about dark matter. And the message I want to leave in your mind is that dark matter, the existence of dark matter through gravitational interactions, is very well established astronomically, using astronomy, and is really now presenting a serious problem in particle physics. That's point number one. And point number two is dark matter really makes the universe look the way it does. It makes the galaxies look the way they do, clusters look the way they do, and on the largest scale, the way things happen. And it's all these invisible people living in our house. Okay, so that's part one. So what we do and don't know about the properties of dark matter, and what we're doing to find out what they are. So it became clear in the 1980s that as the standard model of particle interactions developed, that there really were not many things that could fit the bill for what dark matter needed to do. And what did dark matter needed to do? Well, so electrically neutral, it wouldn't be dark matter if it were charged, electrically charged. It needs to be stable on cosmological times because we can see the quantum mechanical fluctuations in the microwave background. We can see dark matter in 13 billion years ago, and we can see dark matter in galaxies now, or 1 million years ago, because the closest galaxy is 1 million light years away, or 3 million light years away. So it can't decay much. It could decay a little, I suppose. One problem that you always have when you talk about dark matter is among people who work in the field, we say it doesn't interact, or it doesn't interact much. That's kind of code for saying it doesn't interact electromagnetically, weakly, strongly, or supersymmetrically or whatever, too much. The interactions are small. It does interact gravitationally, as I've described, just like everything else. So no interactions. Dark matter needs, if it's going to play its role in the early universe, it has to come into thermal equilibrium early in the universe. So it has to have some interaction, and maybe the laws of physics change, but that's not a very palatable solution. So there is pretty strong hope, I would say, that dark matter has some small interactions by the necessity for it to do its thing in the formation of the universe. And then it can't be too baryonic, meaning it can't be too much a part of the standard model. It has to be something in addition. Okay. Now, there's an enormous amount of activity looking for dark matter that I'm not going to be able to describe. There are a lot of experiments, both on the ground, cosmic rays, spacecraft, observationally, huge theoretical, and I just put a list to give an idea of the level of effort. It's probably numerically a quarter of the particle physics community is involved in dark matter one way or another. So I'm not going to try to be comprehensive, but what I want to do is give the thread of the story from this time when dark matter became a particle physics problem up until now, and then conclude with some opinions. Experimentally, from the particle physics view, there are kind of three big ways of accessing dark matter. There's letting it bang into something here on Earth and measuring the something recoiling. So you can let it bang into a nucleus. And that's experiments like CDMS, which is led by Bernard Sadler here at Berkeley. LUX, which is now a big Berkeley contingent involved in, and ADMX, which John Clark is a major player in. ADMX actually uses photons in the form of magnetic field as the target. So you have this big old magnetic field, a dark matter particle called an axion hits the magnetic field, gets absorbed, and emits a photon. You catch the photon in a microwave wave cavity. So method number one, you let it hit something and look at whatever it hit. Method number two in a wide class of models, but not always, dark matter can annihilate with itself, or if there are several different kinds of dark matter particles, other dark matter particles, can annihilate and create normal matter that can be detected. This would presumably happen where dark matter is densest, which is at the center of the galaxy, but it's not excluded that there are other pockets of places where dark matter is dense. So there's the idea that one could look for dark matter in the form of particles coming from space, which we call cosmic rays. And so there are a bunch of experiments doing that. IceCube is a Berkeley experiment as well, Fermi. And so I'll say something about that. And then you can just make it by banging particles together really, really hard, and hopefully a dark matter particle comes out in a way that you can see it in a particle detector. And this is what the Large Hadron Collider is doing. And there's a very long history of looking for new particles in this way, going back to the Tevatron and LAP and earlier experiments. So these are the three ways of looking for dark matter. I'll say a lot about this, and not too much about this. You have local experts that you can consult, but I'll try to give you my opinion of how these things fit together. All right, so not all of these ways are the best ways to observe dark matter. And my opinion is that observation of dark matter really starts with a nuclear recoil observation. And that means you take a bunch of matter, like germanium or xenon, and you put it somewhere isolated from other kinds of interactions. Dark matter doesn't interact much, so it's able to penetrate through shielding and mountains and oceans and the atmosphere. But every once in a while, it hits one of the particle that you isolated, causing it to recoil. It's a normal nucleus, so it loses energy in the normal way, and I'll say a lot more about this, and you detect it. And that, to me, is what it really takes to begin the discovery of dark matter. Now, there's an analogy to this method in the discovery of solar neutrinos. So solar neutrinos were first observed about 40 years ago by Ray Davis using a similar technique. And he observed about 1/3 of the neutrinos that you needed to observe that were expected from the sun, and just by counting neutrino interactions. And this was a very puzzling result, and those of us who came of age in the 1980s heard a lot about the solar neutrino problem. What it really took to make the convincing argument that solar neutrinos were actually neutrinos that were coming from the sun was an experiment, first Kamiokande, then SNO, where Kevin Lesko was one of the main instigators. Super Kamiokande were able to image an electron that had been hit by the neutrino and recoiled in the direction from which the neutrino came. And SNO in particular has a beautiful picture of the sun taken by neutrinos. And that's what the smoking gun is for both solar neutrinos and for dark matter, is you build some huge detector, very carefully instrumented, you put it a couple of miles underground, and you can correlate events with the direction of an astrophysical object, where there is no way that any background particle of normal matter could make it from the surface down to where the detector is. And I'll come back to this in a minute. So I really consider nuclear recoil, particularly the correlation with an astrophysical phenomenon, as key. Now, 10 years ago, or 15 years ago, when we started AMS, which Bob was kind enough to help us with, and the $100,000 he gave us, we got this experiment going by promising that $100,000 to like 30 different people. And then they used the promise of our money to get money, and it was, in the beginning, experiments are kind of like these massive pyramid schemes. And the guy that gives you the first $100,000 gets the whole thing going, so thank you. We thought we had some really low-hanging fruit because really the theoretical expectation was that dark matter would annihilate to heavy particles, and then the heavy normal matter particles, and then those particles would decay with very discernible or very predictable energy signatures. So you'd have a spectrum of, for example, cosmic ray electrons, and you would see a very clear peak or a Jacobian peak from a two-body decay. And the expectation was that you really didn't need to understand very much about the background in order to just see this spectral feature. Turned out that didn't work out the way we expect, and now we have to do actual work to understand cosmic ray propagation, to look for dark matter in cosmic rays. And even then, I think any kind of observation of dark matter only in cosmic rays will be very exciting. It will be a hint, but it will really inform this kind of experiment that we'll go out and see it on Earth. Finally, collider physics, from the beginning, the SSC era, has always been about making new particles. Any kind of new particles, supersymmetric new particles, technicolor, which may or may not be dark matter. And the Large Hadron Collider is going to start its second run pretty soon. Well, they've started already, but it's early days and it's a little bumpy. And they may see new events, but we won't know those are dark matter particles because we don't know that they are the same thing that's floating around in Andromeda, making the stars orbit the way they do. Again, it would be very valuable to know the mass so that these experiments could be better designed. So that's my opinion. Okay, let me tell you about nuclear recoil experiments. So I told you earlier that the density of dark matter is about 0.4 GeV. Proton weighs about a GeV. So that's 40% of a proton mass per cubic centimeter. Where we are, and that's measured by looking at how stars bounce up and down near us in the Milky Way. So that's a pretty well-known number, known to about 10%. And if we guess a dark matter particle has about 100 GeV mass, the mass of 100 protons, that tells us that there's about 4 thousandths of a particle, 4 per liter particles here on Earth. They're moving around with a velocity of about 10 to the minus 3, the speed of light. So that's just the velocity that you need at our orbit in the Milky Way. And that's because dark matter is cold, meaning it's non-relativistic. And we can guess it has a cross-section of about 10 to the minus 45, which is kind of the range of cross-sections people think about now. So what's the decay rate, or what's the interaction rate? Well, if we have a target that's a kilogram of nuclei, which have a mass of about 100 protons. So xenon, for example, is 136, germanium is 76, argon's about 40. So we'll just say kind of A equals 100. That's about 10 moles in a kilogram. And so there's the normal rate formula. And you get about 2/100ths of an interaction per kilogram per year. And that sets the scale of current dark matter experiments that are here on Earth, like CDMS or LUX. You kind of need 100 kilograms of target to see a few events per year. So it's a tough game. It's a very, very tough game because a lot of strange things happen when you talk about bazillions of particles going through a detector over the course of a year. And having to control backgrounds down to that level is very difficult. To give you a more visual example, if those numbers are correct, in this box is 1 dark matter particle. Right now, this is a box of dark matter.
Thank you.
You may keep that. It's trademarked, and the universal product code for dark matter is on the bottom. In that, if you look at the box, and you're welcome to afterwards, you can pass it around. I have another one for you. If you look on the back of the box, there's an apportionment of how many particles of air, neutrinos, photons are in that box, and it's moles or fractions of a mole. And so if you're going to look for dark matter here on Earth, you've got a lot of normal matter that's just around causing trouble, and the event rates are low. Okay, so another good thing to think about, and this is particularly aimed at graduate students who are studying for their candidacy exams or whatever you call them here. You should know how to do this calculation. Here's a normal matter nucleus. Here comes a dark matter moving with some velocity 10 to the minus 3. They're going to hit. And you want to know how much energy is this thing going to transfer to this thing, given that that's going at 10 to the minus 3, the speed of light, and has a mass of 100 protons. So you know what to do. You go into the center of mass frame. You choose some scattering angle theta star. You transform back into the lab frame. And then you calculate the velocity transverse, which is just this velocity times theta star and the boost velocity along here. And you square both sides, and you wind up with this expression, which is the reduced mass times the velocity squared times some factor having to do with this angle that's between 2 and 0. So the most you're going to get is 2 times this. In the most efficient case, where the dark matter particle and the nuclear particle it's going to hit have the same mass, the reduced mass is 100 GeV, or 100 GeV divided by 2, that's squared. So the largest energy you're going to get is 100 keV. And in the world of particle physics, that's not a lot of energy. And in fact, this velocity is not the dark matter is not monoenergetic. It has a Maxwell-Boltzmann distribution that's spread out over with a sigma of about, a dispersion of about 200 kilometers per second or 300 kilometers per second. So the actual energy spectrum is very steeply rising as one goes down in energy. So the coin of the realm is really being able to detect these recoiling particles with 10 or 5 or 1 keV of energy. So not a lot of rate and very low energy recoils. Okay, so these ideas were coming together in the mid-1980s, and I think it was in 1987 or 1988, I was at a conference in Morjand at a ski resort with my advisor Felix Bohm and a bunch of other people. Bernard was there, and we heard a talk about this from a guy named David Spergel. Now, David's argument was that we should be looking for 100 GeV mass-ish things that could be dark matter, but also would serve the very, very useful purpose of collecting in the center of the sun and cooling the center of the sun a little bit enough so that the solar neutrinos would not be produced as much as expected, explaining the solar neutrino problem. And this is the first example of the abuse of dark matter. Anytime anyone has an idea for dark matter, there's the immediate requirement that it solves some other problem, either the solar neutrino problem or the hierarchy problem or the naturalness problem or some other problem. And it's not enough just to be dark matter. You have to be doing something else. Anyway, late in his talk, he mentioned that you could look for this particle now, these particles now, using existing experiments like the one I was doing for my PhD thesis, which is shown here. So this is a wonderful thesis. This is an experiment to measure double beta decay. I mean, a wonderful topic. I don't know about the execution. So this is about as tall as I am. And in the center are 8 diodes. So I wrote my PhD thesis on 8 diodes. For those of you who are not electrical engineers, diode is like the simplest electrical element. It's just a little thing that lets current go one way through it. But you can use them as particle detectors, and I was trying to look for this very, very rare process called double beta decay. And it just happened that in order to look for double beta decay, the 8 diodes, which contained the material that would decay and also the medium in which they were detected, had to be shielded, very, very clean, copper shielded. You know, my so that it didn't have a lot of uranics in it. And then this was all underneath a mountain in Switzerland in the San Gotthard tunnel. And I had been running it for about a year, and I was writing up my thesis. And Mr. Spergel mentioned that if you took experiments like this and you looked at the very lowest energy part, what you would be sensitive to is a germanium nucleus that's hit by a dark matter particle and recoils. As it recoils, it knocks electrons off the other germanium nuclei, and that's the signal these diodes were designed to detect. and you could actually look for dark matter in this way. And he actually mentioned our experiment. We had another a competitor experiment that was Mike Witherall, David Caldwell, and Al Smith from here. They had a kind of a different approach. The experiments, well, theirs was actually better, but they were comparable in size. So we all went scurrying off, I quite unhappily, because I was going to get my thesis done and then go to Wall Street. Didn't work out. Anyway, we turned down the threshold and we measured for about a month, and we were able to show, we didn't see dark matter. And here's the low end of the spectrum. So these are our data points, and this is counts per kilogram per keV per day. Now, to give you some idea, I showed the spectrum to Rick Gaitskell, who's alumni from here, and one of the real leaders in the dark matter field. He's British, and I was kind of telling him what a crappy experiment this was, and he goes, "Whoa, well, that's, old man, that's not so bad." And then I pointed out that this was day and not year. So current dark matter experiments, if this were year and the background were at this level, it'd be a horrible experiment, okay? But back in 1988, when you're first, you don't have to do a very good job. And what we were able to show is that as a function of mass, the interaction cross-section had to be above this line that's shown here. This line is the expected interaction cross-section of a neutrino that was very, very heavy, 10, 50, 100 proton masses. So immediately we were able to show that one of the ideas of the time, that there was a fourth kind of neutrino, was not dark matter, was not what was responsible for dark matter. So that's shown right here. So that was kind of an exciting result, and I wrote up my thesis and did other things. At this same Morion conference, dark matter was really starting to attract a lot of attention. And I remember sitting at a table with Bernard Saudelet, Blas Cabrera, David Caldwell, and there was another person I remember being there, maybe it was Felix. But the discussion was how to do better than this. How to do better than this. Because everybody recognized that this would be very, very bad to try to look for more sensitively for dark matter without a technological improvement. What they all realized was what happens if you really look at the microphysics, a dark matter particle comes in, it hits a nucleus and bounces off. That nucleus bounces through the crystal lattice, for example, in germanium, knocking electrons off, but also bumping into the other nuclei and causing vibrational waves, phonons, to propagate through. And in fact, more of the energy went into phonons than it went into electrons. And that was a very powerful discriminant because most of the other backgrounds, photons, electrons, interacted by hitting the atomic electrons, which would just knock off other electrons and not create photons. So the idea then was to make a detector that could measure photons or heat and the electrons, and then you collected events and you made a plot where there's heat here, and total energy here, and then fraction of energy in electrons here. So for the pernicious backgrounds, electrons, photons, cosmic rays, you would expect the events to be here. And for neutrons and dark matter, you would expect the events here. And that was a very, very powerful discriminant. You only had to measure these incredibly low energy phonons. So they turned to and did it, and over the next 25 years, really pioneered a remarkable technology. So this is their diode, and on the other side are some electrodes for picking up electrons, and on this side is an array of transition edge superconducting junctions, really thermometers. And so the phonons would be absorbed there and collected as energy, enabling them to make the plot. And this is, this is a great idea. This revolutionized the field. The rub is that this has to operate in a helium dilution refrigerator at millikelvin that has to be made out of super duper high purity Swiss cleanliness grade copper in the bottom of a mine. So there was just an enormous logistical challenge in getting this generation of experiments underground and operating because they were just much more complicated than 8 diodes. Other experiments adopted this technique, either using electrons and scintillation light or fast and slow scintillation light. But the thing that really kind of broke it open was the idea that you measured energy in 2 different ways, and that really discriminated against the dominant forms of background. Okay, so it's what, 27 years since 1988. Ask the question, like, how much better, what did this get you, okay? And I've made a plot here. So this is my data from my experiment, and here are a couple of recent results from CDMS and Lux, and the improvement is by a factor of 10 billion. So these experiments are a factor of 10 billion better than mine. And this really gave me pause for a couple of reasons. You know, when we talk to lay people about neutrinos, we say, yeah, neutrinos, they don't interact much. You know, they interact so little, they go right through the Earth. In fact, they interact so little, you could line up 200 Earths and put neutrinos through, and they probably wouldn't interact. And they really just don't interact much. We are now in the position where we are looking for a particle that can go through 2 trillion Earths without interacting. And so this is just way different than anything else we know about, and has really made me step back and reassess. Interestingly, this experiment also aims to measure, my day job with this experiment was to measure double beta decay in germanium-76. And so kind of an interesting question is, how much better have double beta decay experiments gotten over the same 25 years? And the answer is a factor of 30. Okay, and that's not for want of trying. It's just the nature of double beta decay is the 2 energy trick doesn't work, and it's all about obtaining large amounts of obscure isotopes, and that's just much more difficult. Although experiments like Quarry, Majorana demonstrator will come quite soon. Quarry is running now, looking for double beta decay, and so I think like a factor of 300. But still, 10 billion, you know, that's just an enormous improvement. Okay, so a few years ago, I was casting about for, you know, what the next thing to do, given that there were already these great experiments counting neutrinos. And I mentioned to you before that the really key thing was the correlation with an astrophysical phenomenon. So I thought, let's start by thinking about how to do that. So here's the solar system. There's the sun, there's the Earth, not to scale. The Earth orbits the sun, as most of us believe. And the whole mess is moving through around the galaxy at about 200 kilometers per second. So the dark matter is thought to be relatively static in comparison. So in addition to the Maxwell-Boltzmann distribution of the dark matter in its rest frame, we're moving through it at some fraction of the velocity of light. And so as the Earth goes around the sun, the Earth's velocity vector changes with and against this prevailing dark matter wind during the course of the year. So at this point, when you're moving against the wind, you expect fewer events, or smaller energy transmitted to the detector, just because relatively the dark matter is moving a little more slowly, and later more energy. And so if you look at the energy spectrum at different times of the year, I've notionally drawn them here. So it's moving back and forth, just the Earth's motion around the sun. And experiments typically work by counting events above some energy threshold. So if you're just counting, you'd expect to get more events in December and fewer events in June. Okay, well, that's a great way to look at it, and experiments pretty routinely do this. And in fact, one experiment, Dama Libra, claims to see dark matter annual modulation over a course of a number of years, 7 or 8 years. And nobody can quite figure it out because their dark matter detection rate is way higher than what any other experiment measures. In fact, their detection rate is excluded by many experiments. So it's kind of a mystery. A lot of other things vary through the course of the year, temperature, humidity, rainfall, and so on. But there's no clear thing that they're doing wrong. The collaboration is not terribly communicative. So this is a result that people kind of don't know what to do. So in thinking about this, my colleague, I was working on this with Steve Allen, and I were decided, okay, we're not going to touch that. What we're going to try to do is make use of the fact that the Earth also rotates around its axis. So during the course of a day, dark matter would come from different directions. So at noon, it might come from there, and at midnight, it might come from there. If you could measure the direction of the dark matter particle and show that it varied as you would expect during the course of the day, then you would have a real smoking gun, and it would be on a day scale and not a year scale. That sounds great. The problem is you're using dark matter hitting normal matter, so you really need to create a detector where you can measure the recoil direction of the normal matter, which is no easy thing. Here's a little picture of it. I've chosen 42 degrees latitude. That's where Boston is. We're here at 38, so it's pretty much the same. And so you'd see bumping along, knocking off electrons. And then a high electric field pushes those electrons. Here, there's an amplification gap, just two meshes with a large in between them. Proportional multiplication takes place. Astronomy grade CCD cameras, not terribly expensive. From an instrumentation point of view, particularly for a low background experiment, this is a really nice technique because there's relatively little mass inside the vessel where the target gas is. There are very few penetrations where you would have to worry about leaks through the vessel. And then all of the electronic channels, instead of having armies of graduate students solder from positrons and antiprotons from electrons, and an electromagnetic calorimeter to measure the energy of electrons well. So this took 15 years to build. It was a terribly difficult struggle at every stage. And this is the result for electrons and positrons. So the energy spectrum for normal cosmic rays goes like energy to the -3 power. So all of these are measured by energy cubed. And what you see is something that looks relatively flat in both cases. And if the process I was talking about took place, you would expect to see bumps at the same place in these two plots. That unfortunately didn't happen. And we're reduced or stuck with, does this count rate agree with expectation? The problem is nearby us, we have two pulsars. Pulsars are highly charged magnetic neutron stars that are spinning around, creating a pulsar wind in a large magnetic field that results in the acceleration of electrons and positrons. In the diffusive propagation through our galaxy, electrons and positrons go about, high energy, go about 2 kiloparsecs before they shower and disappear. And so within that range, there are two objects that are thought to produce very high fluxes of electrons and positrons and just muddy the waters. So now what we need to do is understand the cosmic ray propagation using boron and carbon to calculate the diffusion constant. We need to, and this is explained here, we need to measure the ratio of beryllium-9 and beryllium-10 that tells us the confinement time of cosmic rays in our galaxy. We haven't produced a result for this, but one's coming, and there will be measurements up here. And so hopefully that will give us a better idea on the expected rates, and maybe we can find something just by counting. But it would not be as compelling as a spectral feature. In the decays of W's and Z's and other particles, antiprotons come out. That's shown here. So this is our measurement of antiprotons. Again, it conforms pretty well with ordinary sources of cosmic rays, but there are large uncertainties, primarily due to the antiproton production of protons hitting interstellar helium, and then propagation uncertainties. So the message with the AMS cosmic ray experiment is we're really going to need to do a lot of work to understand the nitty-gritty of cosmic ray propagation, which is a good thing to do, and probably something we should have planned in from the beginning. This is another calculation with the same data showing different uncertainties, so it's pretty murky. My hope is really in antideuterons. So in the fragmentation of, for example, Z0s, every 100,000 events you produce an antideuteron, a bound state of an antineutron and an antiproton, and that would be maybe not quite a smoking gun, but certainly very interesting because the astrophysical backgrounds are expected here, and the rates from different dark matter particles are more up here. And so AMS and GAPS, which Steve Boggs leads, are both experiments that in the next 5 or 6 years should be able to measure antideuterons if they. Few words about the LHC. The LHC will be starting to run 2 very, very soon. Well, it's not as bad as I expected. I was all ready to, okay. LHC is starting run 2 and has not observed candidate dark matter particles yet, but there is hope. This will essentially double the energy. Just a remark, combination of LHC non-observation with non-observation of cosmic rays and non-observation nuclear recoil require detailed knowledge or models. So we're really, by not observing things, we're really not narrowing a lot of parameter space very well. I just want to mention that in addition to just making dark matter particles by banging things together, The LHC also can make particles that undergo, normal matter particles that undergo rare decays, whose rate could be changed by the presence of dark matter indicated in these Feynman diagrams. This is a measurement of the strange B meson to mu plus mu minus that was done by LHC B and CMS. And as time goes on, this will accumulate, and this is another rate measurement that could give an important hint. Okay, the road ahead. I would categorize the experimental situation for dark matter as a hot mess. There's an enormous amount going on. Consistent things really aren't coming out. Very fortunately, the agencies who fund this are really committed to it. So this work will continue. But here's a summary of the things I've just told you. This may sound bitter and angry, but it's not. This is science. And this is what happens before you discover something really, really important, is you have some kind of hot mess and a lot of people get interested and resources flow. For myself, I mentioned earlier that dark matter is always kind of punished by having to solve someone else's problem. Well, I'm done with that. I'm just going to look for dark matter. I'm not going to worry about the integrity of the standard model or the baryon asymmetry of the universe or the strong CP problem in the strong interaction. Other people can do that. So I've started looking for dark photons with Richard Milner at this crazy free electron laser at Jefferson Lab. This is through a process called kinetic mixing. And this is really a low energy experiment. And the theoretical basis for this is so broad that it's really just another place to look for dark matter, and I'm not paying any attention to the validity of the underlying theories, which, or the beauty of the underlying theory, which Frank Wilczek, my colleague at MIT, characterizes as tasteless. Okay? So anyway, another thing I'm thinking about are primordial black holes. I know this is not a popular idea, but I'm really done worrying about the integrity of the standard model. So to conclude, and I'm run over, I'm sorry, but to conclude, dark matter makes the universe looks the way it is. Factor of 10 billion improvement in any experimental endeavor is impressive, but gives one pause, and it's given me pause. The situation now is, I'll use the term hot mess. It's a great thing to go into if you're a student, because you want to be in something that's confusing and uncertain and where people are doing lots of different things and you'll learn a lot of different physics. I can elaborate on the need for directional or astrophysical phenomenon if anyone wants to like, but I'll stop there and thank you.
Thank you for a great lecture.
Yes.
Yeah, so you spent most of the talk talking about particles of dark matter, but I would think that there would be conditions under which the dark matter might condense, or the thermal conditions such that it keeps the particles from condensing. And then in your final slide, you talked about black holes.
Yeah.
And I guess part of my question is, how are black holes related to dark matter? In the sense that, are you proposing that maybe that's condensed dark matter?
So, well, yeah. So in the very early phases of the universe, there's a lot of energy locked up in the space-time structure of the universe. And if that energy is high enough, little chunks of space-time just kind of collapse into these little black holes. Now, the little black holes evaporate, so they can't be too small. We haven't seen them in experiments that were designed in the 1990s to look for dark matter as Jupiter-sized or failed stars or things like that. So there's kind of a range over which this could happen. Now, this is not particles. This is some chunk of space-time that's collapsed in on itself. Not a popular idea, and I'm sure there are about like 8 people who are going to tell me that this is a complete waste of my time even to think about. But it's there. As far as condensing, so there are pictures where dark matter is not smoothly distributed. There can be dark matter waves that are rattling around in the galaxy. There can be pockets of dark matter, and so there's an enormous amount of thinking going in that direction. I just don't have time to talk about everything. Oh, yeah. Well, the answer to the second problem, the second question is, it restricts what you're going to look for. So if you say, well, I'm going to look for primordial black holes, a lot of people will say, well, but that doesn't help. I mean, the standard model, we need to understand what the next energy scale is, da 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 da, and that's what I've been doing. That's what WIMPs are all about. They're supposed to be supersymmetric particles, and supersymmetric particles are supposed to solve all these problems, and that's great. And there's an enormous community of people doing that. About you wanted me to comment on the ultralight. So the dark forces theory, I mean, originally were developed to solve a whole bunch of problems, to explain Dama, explain these gamma rays from the center of the galaxy, preserve supersymmetry, and that's all great stuff. But the theoretical underpinnings are just so broad that it's really just kind of a statement of look for very low mass, meaning 10 MeV to 2 GeV gauge bosons that interact like a photon. Well, axions, I mean, again, axions, the interesting thing is there are not a gazillion axion experiments. There's one, and it's a really good experiment, and it's just going. It's just going. The agencies support it really well. It's just a hard thing. So axions are a great dark matter candidate. Certainly, my colleague Frank Wilczek was very upset when he saw my little red box that axions aren't on it. But I'll make another one. He'll be okay. He'll get over it. But so yeah, I mean, I'm certainly not dismissing it. I'm just talking about more of where I'm going.
Louder.
Absolutely. So the question is, if we see an annual modulation, meaning the count rate varying through the course of the year, if our picture of how dark matter is distributed in the galaxy is correct, yeah, we know the phase very well, and we know the period very well. And this experiment, Dama Libra, gets the phase pretty close, which makes it compelling, but it's completely inconsistent with anything else. And there are some very tortured models that make it consistent, but none of them have come to fruition. Well, yes. Yeah. Yeah. But a lot of things happen on an annual basis, like taxes that aren't related to dark matter. Yes. Yeah, yeah. So I think if you got 12 theoretical astrophysicists who work on dark matter in a room and ask them that question, you'd get like 15 different answers. I mean, and it's not that they're not smart. It's just that we really don't know. And there are a lot of different pictures about what could be happening. There could be these caustic waves that move back and forth. There could be, blobs that. Excuse me? Well, I mean, yeah, there are. These rotation curves kind of limit what that picture is, because that tells you with some granularity how dark matter is distributed. But we really need to figure out what it is, and then we can start answering questions like that. Right. Right, and there's a lot of work going on the ADMX experiment. I mean, so the question is really about the technology of how fast the axion experiments, which have to scan through frequency up to a certain sensitivity. Essentially, you're integrating a radio signal or a microwave signal for a long enough time to get to a large sensitivity. And the sensitivity of this experiment is incredible. It's like 10 to the minus 26 watts. And so the question is, what do you do technologically to scan faster? And that's, we were talking about this at lunch. That's lower noise detector, higher magnetic field. And those are certainly being undertaken. And I mean, that experiment is really singular. It's really the only experiment to do it. And part of it is there are very few people who know how to do that kind of experiment.
So, Peter will be here for a little while after the questions. I just want to thank you for the.
Thank you.